Okay, thank you all for coming. My name is Artemy. I'm a little bit outside of the field, although I've worked a bit on information theory and machine learning. But a lot of my work is more related to things like non-equilibrium thermodynamics. Lately, I've been getting more and more interested in AI interpretability, and excited to see a lot of kind of like classic information-theoretic ideas gaining traction and getting applications. So I'm going to proceed as follows. First, I'll give you a little bit of an introduction, motivation, and then I'll give you some background on what is the information bottleneck. And then I'll discuss some alternative proposals that I've been thinking about and some results on a toy model. So this is very, very new. Like, I made some of the plots today, but I've been thinking about this on and off for a while. And I'll finish with some future ideas. I have a question. Who of you is familiar with the information bottleneck idea, just so I know? Okay. Cool. Okay. It's not going to be super technical, but that would help. Yeah. So the basic setup that I'm going to consider is very general. We have some input X, and we have some output Y, and they are related by a stochastic map or channel, and we're thinking of the setting where we want to predict Y from X. So examples might be input and output of a neural network. It might be like a stochastic dynamical system, so X could be the set of past trajectories, and Y could be the set of future trajectories, whatever you want. Right, and I'm going to use this concept a lot during my talk, which is a minimal sufficient statistic, which I think many of you are familiar with. So we say that a function of X is a minimal sufficient statistic, let's say for Y, if it satisfies these two properties. So the first one is sufficiency, which basically means it's sufficient for me to know f of X to predict Y. I don't gain anything else by knowing X. And we can write this in this, I don't know if there's a pointer, but we can write this in this conditional distribution form. And the other thing we want is minimality, which basically says that f is a function of every other sufficient statistic, or can be written as a function of every other sufficient statistic. Okay, and because for example, like x is a sufficient statistic for itself, of course, but it's not the minimal one. And we can think of the minimal sufficient statistic as a kind of compressed description or representation of the distinctions that X makes about Y, the information that X carries about Y. And we can also think of it as a kind of macro state, right? And we can also visualize it. So as I'll discuss later, minimal sufficient statistic sets up an equivalence relation between X, and that's a kind of coarse-graining. And in dynamical systems, I should add, which is kind of a major interesting area of application, these minimal sufficient statistics of the past to the future are called causal states. That's just terminology. So we can also characterize, yes?
Just wondering, on the definition you had for minimality, could I alternatively think of it as if f is a minimal sufficient statistic, then there's just a permutation function that relates it to every other minimal sufficient statistic?
Yep. Yeah.
Okay.
Yeah. I mean, I think that would you could derive that from that easily, right? Because every sufficient statistic, every minimal sufficient statistic has to be a function of every other one. Yeah. Mm-hmm. We can also think about this in information-theoretic terms. Here we need to think about a distribution. Typically, we need to think about a distribution over X, whereas before we just thought of the channel. But let's say we have a distribution over inputs and outputs. And we can write sufficiency and minimality in this information-theoretic way, which is saying basically that the conditional mutual information between X and Y, conditioned on the minimal sufficient statistic, vanishes, which means they're conditionally independent given F. And F has the smallest mutual information of any such function that satisfies sufficiency. And this is a convenient form to kind of express this, maybe a more quantitative information-theoretic form, because now we can think about approximate minimal sufficient statistics. So this is a very, very, in a way, very hard requirement, right? We're sort of requiring that F captures every single tiny distinction about Y that one can capture. And not only is that sometimes very, very fine-grained, but it's also many times quite infeasible to estimate or to calculate. So if we're thinking about the trajectories of a stochastic dynamical system, like we're never even going to sample a significant fraction of all past trajectories and future trajectories. So we can't really know if these conditions are satisfied. So there's a natural idea that, okay, we want something like epsilon close to this, and I'm going to call that approximate minimal sufficient statistics. And we can think of them as kind of optimal ways of coarse-graining X if what we care about is Y, right? Optimal ways of forgetting about the past if we care about the future, for example. And I'm going to kind of refer to the problem of defining and finding these as information-theoretic coarse-graining. That's probably like, that's actually a much broader term, but for the purposes of this talk. So what are some of the applications? Like if we could do this, if we knew how to do this, then we could find robust causal states in dynamical systems and large machine language models, for example. We could also in biological systems and neural systems and so on. And we could also quantify, it's been argued that the information captured by the minimal sufficient statistic about the past is a very natural, let's say about X, is a very natural measure of information theoretic complexity, of how complex is the process or this map. Yes?
Can you say what you mean by robust causal states? Because it seems like this information theoretic sufficient statistic may be like some gross function of like most other stuff in the system. Like it doesn't feel like it's a state of the system itself. It's something else.
So we can think of I think we can think of causal state. This is a bit of a term of art, but we can think of causal states as like the outcomes of F, right? So it's macro states basically, macro states for the purpose of predicting. And by robust, that's another loaded term. What I mean is kind of like smoothed or they don't So for example, a minimal sufficient statistic, if I change one of the future conditional distributions by a tiny amount, that can change my minimal sufficient statistic. But so it's this would be presumably, if it's approximate, it would be more robust to that. And another thing we want to do is we want to kind of, if we have some measure of how approximate we want this statistic to be, then we can vary that parameter and we can kind of sweep across different coarse grainings of the system and see what are the natural scales, right? What are the natural kind of coarse grainings that emerge? And finally, this is something I'm particularly interested in, is we may be able to find kind of optimal ways of blurring or coarse graining the system. So this is familiar to some of you from renormalization kind of ideas in physics. Recently, they've also been very popular in machine learning, and they've also been kind of formulated in this way that we want to blur some kind of microscopic details while preserving information about macroscopic observables or something that we care about. Okay, so if we could formulate it in some kind of optimization principle, we might be able to find these coarse grainings. Okay, so I haven't necessarily solved all of these, but this is some of the things that we could do, and I think there's others also. So the questions that I'm going to try to address in this talk is, first, how should we define the approximate sufficient statistics? And I'm going to talk quite a bit about the information bottleneck, which many of you have heard of, and I think many people think that's kind of like solved this problem. And I'm going to argue that it hasn't really solved this problem, and maybe there's other ways to think about it. And I'm going to briefly mention how we could maybe actually then, given some alternative definitions, actually use gradient-based learning or other techniques to find them in really large systems or really large data sets. And I'll briefly touch upon how we can kind of visualize and interpret the coarse grainings that arise. Great. Before I go on, is there any questions? Great. So as I mentioned, there's a kind of very influential, especially recently, it's become very influential way to think about this, which is called the information bottleneck. And remember that I said that in information theoretic terms, a minimal sufficient statistic has these two kind of very natural properties. One, the conditional mutual information vanishes, and it achieves the best compression and best minimizes the information about X. And the idea behind the information bottleneck is that, first of all, let's, instead of thinking about deterministic functions, which is kind of this at best combinatorial huge space, let's think about stochastic channels from X, the thing we want to compress, to Q, and I'm going to use Q as this, sometimes it's called the bottleneck variable. It's kind of our representation of the compressed information in X that's relevant for Y. And we're also going to soften the condition of sufficiency, and we're going to say, okay, we don't need like total conditional independence, but we allow a little bit of eta. And there's going to be kind of a recurring, by the way, I'll give you a preview maybe of something that's going to recur, and something I've been thinking about is like, when we're talking about exact minimal sufficient statistics, there's many, many equivalent ways of formalizing them in information theoretically. These different ways are equivalent, but they suggest very different generalizations with different properties. And I think that's probably common in other fields. But we'll see. So this is one way to sort of soften the conditions, right? We say that the conditional mutual information should be smaller. And we then minimize this objective, which is a linear combination. It can be thought of as a kind of Lagrangian of minimize the information that Q carries about X, but also minimize the conditional information between X and Y once we condition on Q. So the kind of information that leaks through, let's say. And as beta goes to infinity, we can see the last term dominates, so we recover the minimal sufficient statistics. And we can also rewrite this in this simpler form. So by using the fact that Q only depends on X directly, so Q is independent of Y given X, we can rewrite the conditional mutual information as the difference between the mutual information between Y and X, which is just a constant, doesn't matter for optimization, and the minus the mutual information between Q and Y. So how much information does Q have about Y? And we get this very, very beautiful, nice form, which says, we should minimize information about X and maximize information about Y. And many times people plot it on these kind of information plane diagrams where we plot the compression on one axis. So this is like how much we've maintained. So we kind of want to go to the left here and up here. And there's a certain curve that separates the feasible region from the infeasible region for a given input-output map X and Y. Okay? Great. So there's also a different way to think about information bottleneck, closely related but different, which is rate distortion theory. And rate distortion is something that Shannon already thought about, like in his 1948 classic work, and then wrote another paper about it. But rate distortion basically is kind of the classic, well-established theory of lossy compression. If we want to compress something, how should we do it? And rate distortion theory says that we should minimize the mutual information between X and the compressed representation Q, but also minimize this expected distortion function. So what is this expected distortion function? Well, let's say, we're compressing images. So X might be a raw image, Q might be a JPEG representation. And, actually there was a lot of labs that did studies that studied how people perceive errors of different kinds when images are compressed using JPEG, and that could be encoded in the distortion function that basically says how bad is it when I map raw image X to JPEG Q. Okay, and the problem is, we don't really know how to choose this in many settings, or at least we don't think, we do. And this was one of the motivations in the original information bottleneck paper. They said, well, since the rate distortion measure is rarely available, the problem of relevant quantization has to be addressed directly by preserving relevant information about another variable. So we don't know this kind of like distortion function, but we do know many times that we want to predict something. And that seems kind of easier to get a grasp on, right? And it turns out that information bottleneck can be also written in a rate distortion way, but there's some subtleties. So we can write it basically as minimizing the information subject to this distortion function, where this distortion function says minimize the Kullback-Leibler prediction error of predicting y given x versus predicting it using q, which is the bottleneck variable. Okay. Now, the important thing to note here, so we're going to compress, so it's very similar, but it's more directly written in terms of minimizing prediction error, right? And I should also add that, like, maybe this is, I'll say it later, but the important thing is this is not standard rate distortion, because the distortion function itself depends on the coarse-graining map. Because this predictive distribution here is kind of like the Bayesian inverse of the distortion map. So it's kind of like, given how I'm compressing, okay, well, we could think of this as a kind of decoder. The decoder is then optimally adapted to sort of undo that compression and best predict y, which is what we care about. And this actually really changes the setting. So as I'll discuss next, so what arises from this difference? And I should also say that, like, I realized when I was reviewing my slides that maybe I'm coming off as like being really negative about information bottleneck. Information bottleneck has had quite a few successes, especially under certain approximations that have made it tractable. And I think it's kind of, it's more of an inspiration. I don't want to say that it's like useless, but it does have.
I was laughing.
Oh yeah. I'm not saying it's useless.
No one.
This is being recorded, apparently. So it has some limitations. And for me, okay, there's a technical, mathematical limitation, but there's also, I think, a conceptual one, which this space Q, at least under most formulations, is kind of a totally arbitrary space that we map to something that's the compressed representation. And it's not clear how to actually like visualize, interpret, or unpack this representation. And part of that is because Q lives in an arbitrary space. It doesn't have any kind of relationship with X, right? It's not living in the same space as the thing we're compressing. And even if it did live in the same space, the information bottleneck objective doesn't have any kind of notion of similarity. It's completely invariant to, let's say, permutations of Q, or invertible transformations of Q don't change the objective. So, if X is like states of a spin glass or something, then even if we map it to other states of the spin glass, we could completely permute them and kind of lose all structure, and that's just as good from the perspective of information bottleneck. The other thing, which maybe recent success of machine learning tells us we don't have to care that much about, but it ends up with this non-convex objective, unlike regular rate distortion. So we don't actually know how to find the global minimum, right? And I think for kind of like some practical applications, that maybe doesn't really matter so much. We think maybe we have a really good representation or good compression, but oftentimes in the scientific domains, people are applying this and saying like, the visual system is information bottleneck optimal, or this kind of the language, there's, language is information bottleneck optimal. We don't actually know how to find the curve. Like we can just like run the optimization 1,000 times, which is what people do. But so we don't know the fundamental bound. And yeah.
So this algorithm in the original paper, it just finds local minimum.
Yep, it finds a stationary point basically, the Blahout-Erimoto. Yeah. Mm-hmm. Yep. And people don't really mention this also very often. Yeah. And both of them are due to the fact that like D itself, the distortion incorporates the map into it, right? It's not a classical kind of rate distortion problem. Great. Okay, so I'm going to talk about maybe a different way to generalize the concept of sufficient statistics. It's slightly different than information bottleneck. And there's kind of, again, because we're going to avoid this problem of putting the distortion function, the compression map in the distortion function, we're going to get first kind of more interpretable coarse-graining maps. At least we can kind of think about them as working in the original space. And we also transform it into a tractable and scalable convex optimization problem. And we're going to do that actually by formulating the problem. There's the one kind of subtle thing here is I'm not sure if there is one best way to do this. So this is something I'm kind of interested in playing around with. But I will talk about two ways to generalize approximate sufficient statistics. And one of them leads to a regular old garden variety rate distortion problem. And one of them leads to an optimal transport problem. And I'll explain a little bit what that is. And so, like, you know, let's start by thinking of a different but equivalent definition of minimal sufficient statistics, which I think is actually a lot more elegant, which is that minimal sufficient statistic is actually an equivalence class between outcomes of X. Okay, and I think it's kind of this is not that. I mean, this is sometimes people talk about it like this. It's not like the first time it appears, but I think it's even kind of formally it has some attractive features. Like it doesn't depend on this arbitrary function f, which is actually related by invertible transformations to a bunch of other functions. Right? It's a unique kind of equivalence class, and it basically says that x and x prime are equivalent if they give the same predictions for all y. And what that means is also like that kind of suggests a different generalization or softening of the concept of minimal sufficient statistic to define approximate minimal sufficient statistic. And this is the one I'm going to use. We could think about it in terms of joint distributions. We could think about it in terms of channels. It's kind of, there's not a big difference. But we can say that a minimal sufficient statistic can be represented by a channel or joint distribution from X to X, so in the same space, where essentially the expectation of the Kullback-Leibler divergence under the resulting joint distribution is 0. So in a sense, like the only X and X prime are only joined, right? Or they're only linked if they give the same predictions, exact same predictions, and the information is minimal between these. Okay, so. Slightly different, but you know, one of the things that we'll see is like we can. Sorry, this should be x hat given x. One of the things we see is this is going to give us a kind of like interpretable diffusion map or coarse-graining map that sort of you know blurs out the information we don't care about while still preserving predictions about y. And so I'm going to use this to define two kind of alternative coarse-graining objectives, information coarse-graining objectives. One is based on rate distortion, and one is based on optimal transport. Any questions? Yes?
Short question. The x hat is just the coarse-grained version of x, right?
Yeah, but we can think of it as like living in the same space. So it has the same outcomes, but it's the coarse-grained or blurred version of x. Mm-hmm.
This isn't the more general version than the one we showed before. That's going to come next, right? Is that right?
Yeah, this is an information-theoretic characterization equivalent of like a minimal sufficient statistic, but it doesn't mention anything about f. It's just in terms of this equivalence relation. Yeah. It's complete, but this is kind of what I meant. That like it suggests a different generalization, right? So we can, and there's many. So you know, the thing is, maybe I say this. There's others possible. I mean, actually, like you could think about other cost functions here. I mean, some are more meaningful than others, but there's kind of many ways, and they suggest different generalizations. Yes.
So can I think of this channel as roughly a combination of first moving things around which don't matter and adding more noise, which also that.
Sure. So so like at this point, yeah. So at this point, I haven't kind of done the approximation. I haven't softened the constraint. At this point, it moves stuff around that doesn't matter. Like it connects states that give the same predictions about y.
But can't you also add some randomness between the states which make the same prediction?
Yeah, exactly.
Does that decrease the thing, or does it?
So maybe one way to think about this is like we could think of this as a graph, maybe like let's say we can think of it as a directed graph, right? Because it's a kind of it's a kind of weighted graph, and basically it's only two states are connected, like if and only if they give the same exact predictions about y.
So that would be the first condition. That the second one, the minimum
Yes.
condition in this case.
Yes. So that would mean like, because like, okay, if I just want this condition, then the identity map satisfies it, right? This condition basically says like transitions should be like merged to the extent possible.
The maximal graph.
Yeah. 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 Or the most coarse-grained graph or something like that. Yep. So, so let me now say, okay, so this suggests that we just think about this problem of information-theoretic coarse-graining using, as I call the regular garden variety, a rate distortion, where we minimize the information transferred to the compressed representation x hat, but we also minimize the expected Kullback-Leibler divergence between these predictions, right? And so, I mean, here already we see that I think something, I mean, it's kind of, I think obvious once you see it, but ahead of time was less obvious. Like, you don't need to change rate distortion to have your distortion function be about predicting another variable, right? Which was kind of like the Tishby and Bialik argument. You can do it. You can just use Kullback-Leibler divergence. And one way to think about this is like we're not adapting the decoder, so to speak. We're not adapting the decoder to predict y from from Q. We're just using the fixed decoder, and because we're using a fixed decoder, there's a kind of identity relationship between the coarse graining that's going to be preserved. We can also think of this optimal Q as a kind of, I mentioned that as a kind of diffusion. We'll see that it's like given a certain budget of like how wrong I am about mispredicting, how like diffuse maximally in the space of states. And as I mentioned, this is a standard a rate distortion problem with a convex objective. It can be optimized using standard algorithms. There is one thing which is like, maybe we can talk about that in questions, like if y is huge, so if y is the space of all future trajectories, this itself can be difficult to estimate, but we can kind of talk about that. I think there's ways to get around it. And there's a kind of like operational interpretation that I think also helps. There's a couple of operational interpretations, but there's one that I think in this for this audience maybe is helpful to think about, which is we can even imagine like two dynamical systems or two, let's say, machine learning models that have already been they've been trained. We don't mess with them. They're just given as is. And what we do is, okay, we sample an input of 1. We send it across a low bandwidth channel, a bandwidth constrained channel, and then we use a copy of it to make the prediction. And what we want to do is we just want to minimize the prediction error made by that copy. Okay? And what this means is actually like, we can also think of this as a kind of autoencoder, basically. So we're autoencoding inputs to inputs, but the cost function is given by prediction error on let's say some other like fixed network. And we would want to penalize the information passed through the intermediate representations of the autoencoder. Okay. And, we can write the objective for this, for example, if we wanted to do this with gradient-based learning, if we wanted to learn this. And the problem is much easier than information bottleneck, again, because like if we were to do this information bottleneck, and if we do information bottleneck with machine learning, we have to train a separate decoder. And there's a kind of adversarial thing that happens where, one part of it is trying to compress the input, another part is trying to like decode from the input, and it's quite unstable, and it's not very easy to train, as I've seen in my own work. Here we don't kind of have that problem. Yes?
This Q function, should I think of it like a hard clustering? So an X only maps to a single X hat, or can it spread out over all the X hats?
It can spread out. Yeah. Yeah.
It won't?
We'll see some cues.
Okay.
I'll show you a cue. Yeah. It doesn't spread. I mean, well, it spreads out a bit, I guess. Yeah. Yes.
Just to sanity check, like Q is not unique, right?
No. Q is Q. I think it would depend actually on this function. I think in many cases it might be. That's a good question. I think in some cases it might be unique. I haven't thought about that.
Didn't you say it's convex? Yeah.
Yeah. So that would make if it's strictly convex, then the optimum is unique. So you mean the optimal Q, right? Or just Q?
Yeah, never mind.
I mean, we can think of this like, okay, so here, like, if we were trying to, let's say, learn this information-theoretic coarse-graining using a neural network, right? This would be where Q is, and we would be, like, adjusting its parameters over time. So there's many Q. Some are more optimal than others. Okay. Any other questions about like? Yeah.
So going back to another sanity check.
Yeah.
The last slide you showed was, of course, this approximate relaxed version based on rate distortion.
Yeah.
If we go back to kind of the pure unrelaxed minimal sufficient statistic in this kind of formulation, there the mapping from x to x hat is unique, right? Like each x has to go to a single x hat.
No.
You'll still be able to get to a KL of 0 somehow?
That's exactly the idea. So like we can send an x to an x hat if they give the same predictions about y. If they're equivalent under the minimal sufficient statistic.
But for each x, there'll only be a single x hat it goes to. It'll be a delta.
No. So I mean, if it's so x is.
Surprisingly, but I'll take it offline.
I think that's kind of important. Like me and you give the same prediction about Paul's behavior tomorrow. Exactly the same prediction.
Right.
We're equivalent.
Right.
Under the.
And therefore, we would both map to the state that means gives that prediction.
Well, I would map to myself, and I would map to you, and I would map also to Martin, if he gives the same predictions.
Okay.
Great.
Yep.
So yeah, kind of go back. Yeah, I think I am confused. So for the information bottleneck, it's the number of states and then the loss allowed. And so maybe like I just don't have intuition for how that could be non-unique if we allow for like suboptimal prediction given like the number of states.
Yeah, sorry. I mean, I'm not sure, there's an infinite number of possible Q that we're optimizing over them. Like, we're looking for the best compression.
The optimal is unique.
I think the optimal, I think the optimal is generally going to be unique, just because of the convexity of the...
Surprisingly, is if the optimal is an autoencoder, like the solution to neural net problems is almost never unique because you can like permute the units in a layer or something.
Well, so that's different if this is a parameterized family, right? If this is parameterized by a many-layer neural network, we're optimizing over a constrained space of distributions, and that's no longer convex necessarily, and so on and so on. But I think this is kind of not super important whether the optimal is unique or not, so I'm going to keep going. Okay, never mind. Now I can talk about it more.
Whether the optimal is unique, but I think it's bringing up some questions about what exactly is convex here.
The objective is convex, and the feasible set is convex. Right. So it's a convex optimization problem. But maybe we'll
Your computer's just sleeping, right?
You might be that.
Oh, geez. Sorry. Okay. I will. I mean, it shouldn't be because I'm clicking.
Are you out of power?
No.
If you're out of power, you're out.
No. Maybe I don't know if it's. Is it? Okay.
Because I'm also a little bit confused. If you're at like this extremal value of beta, such that you actually want the minimal sufficient statistic, then in that case you'd have this the mapping to a single x hat. No, you're saying not even in that case.
Let's say y has no information about x. So P of y conditioned on x does not depend on x, then we're all equivalent. All the x's are equivalent, and it's going to be like a fully connected. It's like going to be.
I think maybe what we're saying
single class,
is
then it's going to be a single class.
Yeah, because there's the trivial minimal sufficient statistic, which is just null. I mean, so like let's say the past trajectory has no information about the future trajectory. There's only one causal state. So there's only one connected component, of the equivalence relation.
Right. So I guess I would say everything points to that one thing.
Yeah.
But I think you could say formally like each guy maps like a uniform distribution.
I see. Sorry. I understand now. Yes, the P's that. Sorry, I understand. The as I've written it here, I understand. Sorry. I will go back. This is not unique. This is not unique. There's a kind of canonical way so this is not like, there's not one single, when I say tilde can be represented by this channel, I don't mean to say there's only one channel. But there is, I think, a canonical channel. We can discuss what that is to represent it. But so like, here's two channels. One of them, they all map to a single guy. It's a deterministic map to a single guy. Here's another channel. We all map to everyone with uniform probability.
Right.
Okay. So let me keep going. And maybe I'll give you an example. This is a very, very toy model that I just coded up a few days ago. But basically, I drew this maze, and I put a random walker in it. And it's, as Daniel Polanyi calls it, it's grid world. So you can move up, down, left, right. There's a continuous time Markov chain. And all the transitions that are allowed are equally likely. And so as x, we just say, okay, where am I in the maze now? And as y, we say, where am I gonna be after time t, after time 10? Okay, and so in this case, actually, I believe the minimal sufficient statistics are x, like that you can't really coarse, if you want exact prediction, you can't coarse grain, but we can compute the rate distortion curve. So here, as if we're willing to tolerate some misprediction about our state after time 10, by mixing together these different initial conditions, then we can reduce the information we need to transmit about the location of the walker. So here's what they actually look like. We can compute these and show what they look like. So I'm going to show you. These are the optimal coarse graining maps just computed. This is computed using Blahout-Arimoto, the kind of standard algorithm for rate distortion. So here's, let's say this is the starting location. So this is the conditioning x. And we see that as beta drops, so as we care less and less about prediction, so to speak, we start to blur the location. So this is kind of like, we can think of this as a kind of diffusion process that's blurring where we are in the maze without losing too much information, right? And we see that it's actually like, it doesn't have any information explicitly about locality. It only has it through the predictions about y, but we see that it spreads locally, and this kind of answers your question. Like, it doesn't spread everywhere at once. That makes sense. We can compute this for a few different starting locations. We kind of see like how this renormalization or coarse graining proceeds. And one thing we can also do is we can compute like how does the compression and the distortion depend on this beta, on this trade-off parameter. What we find in particular, so this is obviously a toy model, and I've been squinting at it a lot, but if we kind of squint at it together, so we can see like this has local minima, it has peaks. So basically peaks, this is the derivative. So this is the compression. So as beta increases, we need to store more and more and more information. and we make less and less and less prediction errors. Okay, so beta is increasing to the right. This is actually kind of a little bit opposite of this direction, so maybe don't look at this for now. And this is just a derivative. So this is like, as we change beta by a little bit, how does the compression or distortion change? So for example, we see here, this peak of compression. This basically says like, when we're above beta about 10 or 20, we actually don't really like coarse grain at all. And we don't really lose information about the location of the walker. So when we first start losing it, there's a peak because that's kind of like where it starts to kick in. And there's also kind of this interesting kind of characteristic scale. So this is the distortion. So we can think of this as like when we change beta by a little bit, like how much do we like really decrease our predictive errors? Or how much do we, so it's like it's kind of a signature that we're hitting some kind of structure in the system that makes us predict worse and worse and worse. And if we see, I've like, kind of hand wavy and looked at a bunch of these pictures, but we see that this corresponds to, actually I know it corresponds to beta 0.03, which is somewhere around here, which is basically like when the walker leaves the room that it's in, the average kind of walker. So it kind of makes, it's suggestive that it's uncovering the kind of spatial frequency that's characteristic of this little maze I drew.
And do you see that if you increase the room size, then that moves?
We should test that. Yeah. I mean, I think it would be interesting if we could do like hierarchical rooms and see multiple. Yeah. I mean, that would be a natural, but yeah. Okay, so I have 20 minutes, and I'm actually really going through this pretty well. So does anyone have any questions before I go on? Yes.
So this is really fun, right? I'm thinking you could do this on a Sierpinski gasket, if you wanted your hierarchical, if you wanted to see kind of a scale-free renormalization flow.
Like a random walker with...
exactly, like how much do I have to localize on it? You should sort of see like it's a continuous flow. I mean, this is a soft clustering, right? It's not like I've reduced the number of symbols.
Right.
I've just kind of smudged it out. So I'm wondering a little bit, is there a way to recover a hard clustering, like a hard coarse graining from this?
Maybe. Yeah, so you could...
like fuzzy sets.
Maybe. So in information bottleneck, there's this idea that you can replace the compression cost with Shannon entropy of the compressed representation as opposed to mutual information. And it's been shown that that actually finds deterministic clusterings. And so you could probably do that here also. I think it would also, because like then you can't sort of improve the objective by adding noise to the map, right?
I mean, what would be cool is if you could adapt this so that you could actually recover the room structure.
Yeah.
Right, like you'd actually have some coarse graining where you're like, look, you couldn't even see that there were rooms here.
Yeah.
Lo and behold, actually this thing is wandering in 5 rooms. Like that would be.
So maybe I'll show you something a little bit like that. I do think of this, then that's why I keep using this term. I do think of this more like a diffusion process or renormalization process rather than a clustering. Yeah. Because I actually think, But that's I think a clustering. I mean, in a way, hard clustering is useful, but it's very hard to find. It has this very combinatorial kind of flavor. So I'm going to talk about. So there's actually many objectives we could play with, but I'm going to talk another one, which this has been written about recently. It's not a very deep idea, but like rate distortion is very closely linked to something called optimal transport. For those of you who've heard of it, and specifically entropic optimal transport. So I'll explain this in a second. But if we can modify the objective by adding a constraint. So we say, okay, now I want this coarse graining map, and it maps like, it blurs x's into x hats or whatever. But I also want the distribution of x hat to be the same as x. Okay, so I want them to have the same marginals. And this kind of addresses your question, like what if like we're all equal? Do you map it to a single one, or do you map it or do you distribute it evenly before them? So at least formally the information theoretic objective doesn't favor one or the other, but this would enforce, so if the X are uniformly distributed, as they are in the maze, for example, then you have to kind of like recover that same distribution. And
so if X hat, is X hat in the same space as X? Did you say that?
That's key. That's key, yeah. X hat is in the same space as X, yeah. Yeah. And one way to think about it is we kind of, another way to think about it is like we want the px to be the steady state distribution of this channel, right? So like when this channel is mapped to px, like it shouldn't change it. So it turns out that this is equivalent to something called sinkhorn distance, if any of you are familiar with it, but this is kind of an idea from optimal transport. And in optimal transport, we say, okay, find me a distribution where with two given marginals, so that transports like so basically I want a joint distribution that transports one marginal to another marginal while minimizing a cost. And that would normally be written just like this, but then people found out, actually it was kind of for practical reasons, but it's also conceptually interesting that if you penalize an information theoretic quantity, it actually simplifies the optimization problem. So we can think, this is sometimes called entropic optimal transport. So I want to transport in a way like px to px, but not send too much information. And this gives us a notion of, so we can think of kind of the coarse-graining error as a distance. Actually, this is a regular, at least Wasserstein distance is a distance. It's, it gives us a geometry and so on, satisfies the triangle inequality. And so it's kind of an interesting, it's a very interesting field. And here, what does that give us? Well, one of the things it gives us is it gives us a way to write the optimization in its dual form. This is, yep.
So here this cost function D is arbitrary, or?
So as in general, it's arbitrary, and in our case, it's the Kullback-Leibler divergence.
You see, okay.
Yeah, yeah, yeah. And it turns out that optimal transport, many versions of it have this like really nice dual formulation. So we've turned a high-dimensional constrained optimization problem over joint distributions into a lower-dimensional unconstrained maximization problem over these potentials. And I'll talk about kind of what these potentials mean. So it's much more tractable, and it gives us basically these are Lagrange multipliers that enforce the marginal constraints. But in our case, we can think of them as like, if I increase the probability of a given state by a little bit, how much does it increase my cost or this in this case it's this kind of compression cost, right? So we can think of them as, so like, why is this interesting? For me at least, before, I showed you the maze, and now for every like starting point, I can show you the conditional distribution. But what I would maybe like to have is a number assigned to each point in space. That tells me something about that point in space, like a potential. And here, we can kind of think of these potentials as picking out states that are hard to coarse grain. Right? That if I put more weight on them, then my cost increases by a lot. And so I can run this for the 2D maze. And this is, I'm plotting the potential, and what we find is the potential actually picks out things like doors and narrow spaces and stuff. I'm still kind of like, yes? Uh-huh.
It's, you get one potential for every particular X.
Yes. Got
it, okay, thank you. Yeah. So this is like the doors from the point of view of the little guy in the bottom right there.
No, sorry. There's that's the thing. There's just one potential.
One. Okay.
Yeah.
Great, thank you.
Yeah, but it assigns a value to every little x.
Great. Yeah.
Can we just briefly review the sizes of the primal and dual problems here?
Yeah, I mean, so like for a large system, they're both intractable. Exactly. If you wanted to do them as
and briefly, when you said the dual was smaller, that's under some assumption about there being more of something than something else. I want to kind of say it, right?
So it's smaller in the sense that the primal is n squared,
Where n is the size of x?
Yes.
It's n squared variables or n squared constraints or both?
It's at least n squared variables, and then there's some constraints, and there's like two n constraints. The dual is just 2n variables and no constraints.
Okay, so the dual is always smaller. It doesn't matter how big x is or anything.
Yeah. Yeah, but there's another thing which is really useful for machine learning, which is like these we can parameterize by neural networks, right? And so this is, for example, used in things like mutual information neural estimator. If you're familiar,
You're saying the dual is more acceptable to amortized inference, basically.
it's more acceptable to like unconstrained gradient optimization with like highly parameterized models. Yeah, right. So like normally, like of course we can't enumerate x in a large system, but we can parameterize these potentials basically. Mm-hmm.
The situation where the cost function is symmetric is phi equal to psi.
That's a great question. So that's kind of something I'm playing around with. So in my runs, they are equal.
They are equal even though you're using the tail.
Yes. Yes, they're equal when I glanced at them, like up to numerical. I think, yeah. I think in general, you know, this is not necessarily symmetric, so I'm trying to kind of figure out why that is, if it's obvious that it should be or not. Yeah, good question. I have 5 minutes, so anyway, when I wanted to show, I mean, I don't know if this is just something I saw recently. I thought it was interesting. And how to understand this. The way I understand it is like, we can think of this as like the costliness of coarse graining a given state. And if we're in the middle of the room, then it doesn't really matter like if you like, you know, if you coarse grain everyone in the room more or less into like, you smudge them all together, it doesn't really change your predictions. But if you're at a doorway, right, there's like two very different futures that are possible, that are accessible to you. One you go in this way, and one you go in this way. And this actually reminded me of something Daniel talked about yesterday, which is kind of like, it seems in a way related to empowerment or these other intrinsic kind of motivation goals, or there's also a thing called causal entropic forces, which is like, okay, these are kind of the locations where many futures, many non-equivalent futures are available to you, possibly. This kind of may be an interpretation of...
Is it also like irreversibility?
Not in the thermodynamics sense, as far as I know, but...
in the door, right? You go for... Because this walker, right? It goes randomly in every direction.
Yes.
So if it goes in one room, then...
Yeah, we could think of it, I mean, we can think of it as... Yeah, maybe you could think of it as like, you're not going to come back to, I don't know, over the time scale. So this is all like relative to y, which is 10 time points units ahead of... Daniel?
May I offer an interpretation? I mean, when you do Wasserstein distance or related measures, what you're actually measuring is a kind of cost of moving from one spot to another.
Yes.
On average. So in other words, this is a kind of a bit like relevant information type measure. It basically says if you mix the cost of information traded off against a task that you want to fulfill. And now, this type of highlights, not exactly this one, is something you get when you do goal-relevant information, so agents that where you have to track how much information do you need about the goal to make a path. So, and this formalism gives you not exactly this type of map, but quite a related one, highlights doors, because inside a door you need the most information, or you have the most information exchange about before and after the door. So essentially, when you cross a door, you need to take in new information about the goal as you go through the path. So the idea is actually, and I like it that you managed to actually localize that, and you don't actually look at path, because everything about the path is hidden in the Wasserstein or in the sinkhorn distance. But I think that's what's behind that. So the reason you get that is because these locations implicitly store where your information needs to change or where you need to get new information about your path. That's my interpretation of it.
Interesting. Yeah.
And I'm a little confused by that, because if you've observed the previous path and you come to a door, you know the future path. You're going through the door with pretty good probability, right? Like, that's why you went to the door, if you're going to get through.
So this doesn't really have, I mean, I think, maybe I should add, like, in regular optimal transport, we know there's a very beautiful interpretation of these potentials. They're called Kantorovich potentials. And they basically say, if I want to transport, like, bricks from a bunch of factories, which is me, to a bunch of stores, which is Simon, I can either pay trucks to take those bricks, or I can buy and sell those bricks locally, and the potentials are what price I should buy and sell those bricks. Yeah, and you can achieve the same cost without transporting anything, just buying and selling at those prices. So there's a kind of beautiful economic interpretation. Here, I don't know, maybe we should sit down and think about it, because the dynamics are not really built into it, and there's nothing like taking in information. I just think, like, it kind of, I don't know, yeah, but maybe it's equivalent somehow. Yes.
So let's say you did this with an LLM.
Yes.
Okay. And so now I'm looking at words, right? So, like, intuitively, what are the words that have high Kantorovich potentials? They're kind of hinge words of some sort where, or some, I don't know, no, they're not hinge words, there's something. It'd be really interesting to run this on an LLM.
Yeah, like ones that, yeah, it's very interesting. Like, maybe ones that cannot be like coarse-grained into other words. They cannot be like stochastically like denoised into
critical words in the sentence.
I mean, I would think these would be like phrases, but yeah, like phrases that like you don't want to that like if you change something, it gives you really different outputs. I get, yeah.
You're gonna go into a different room.
Yeah, you'll go into a different. If you change one word, you go into the foyer, but you go into the bathroom. You know.
Right.
They're hard to vary words.
Maybe like reasoning words, like but, however.
Yeah.
Yeah, but and however, you would want to put together because they're very similar.
I'm gonna finish because I have 5 minutes left.
Yeah, even maybe a little less. So I mean, there's, the next thing is the walk.
Yeah.
So, like, pressure is.
So we'll bring the projector and all this stuff, and we can just continue. This is a good point. I'll just mention I have very few things left to say. I'll just say, like, there's kind of, once I start thinking about this, there's maybe an interesting way to extend this, I realized, which is, I talked about mapping from coarse-graining, one walker to other locations of the same walker, but we can kind of think about this as two different models and kind of using this to align two different models. So let's say I have one model or map that goes from images to classes, and another one that goes from audios to classes, so it labels the animals that you're saying or the animals that you're seeing. We can actually still define this as a kind of like alignment distance between different predictors, even if they have different spaces. I don't know where that goes. I think it goes somewhere, but I'm not sure. So it's kind of like finding shared representations, basically, possibly under constraints. Or I could translate from like ChatGPT's to Claude's, right? And beyond that, there's like just some kind of technical things that I think would be fun to play around with, like what does this look like for multivariate Gaussians? That's usually like kind of the starting point. Does it give the same decomposition as information bottleneck for that restricted class? Do we see phase transitions in the optimal representations, which is something we see in information bottleneck a lot? I think we would. I don't think that depends on the convexity or non-convexity of the objectives. And finally, like maybe it would be kind of interesting to think about this in terms of renormalization. So we don't necessarily think of this like a one-time map, but what if this is a generator of a flow, or like we iterate this map? Can we kind of converge to can we find critical point, fixed points of it, or can we use it to? So I don't know if that makes sense. I kind of like what we're looking for here is like one step of the diffusion process, but we can think of this as finding the flow, right? That's it. I think, yeah.